Hello, my name is Roland de Domaine. I'm the Vice President Engineering at eSOL in Europe. Today, we will be talking about the OS evolution, and especially the evolution from the monolithic kernel to the microkernel design, and now the more recent, the multi-kernel design. In this presentation, we will go through the definitions of what a kernel is and the different types of kernels that you can find. A little bit of history and how the monolithic kernel and the microkernel evolved, and then the later stage of evolution of the multi-kernel and the considerations around it. In terms of definitions, the kernel is the base of the operating system, which is mainly the low-level services that help all the other applications run on the platform together. And typically, the kernel is running into a privilege mode on the SoC on the chip. This is because it is the only entity that is capable of switching from an application to another, and in some cases, to manage the memory and the resources on the platform. A monolithic kernel integrates not only the scheduler and the memory management, but also all the device drivers and possibly even all the middleware on the platform as well. A good example is the Linux operating system, which contains all the drivers, including USB stack, network stack, file system, etc., inside the supervisor space. A microkernel is exactly the opposite and contains the minimum number of services inside the privileged space. Meanwhile, a unikernel is an emerging name for actually a simple operating system which typically does not have memory protection or memory management support. Sometimes it does. And especially the configuration of a unikernel is designed for cloud computing, where the system will run mainly one application, and the operating system, the kernel, is linked and tailored next to that application. And typically, it runs as a guest onto a hypervisor. The multi-kernel, which we will see again in a few minutes, is a new type of kernel where instead of having a global instance of the kernel and a global instance of the system, the operating system running onto multiple cores, actually the system is split into a runtime for each core, which could be exactly the same code, but working on very dedicated data. And all the cores are independently taking scheduling decisions, but globally working together as a network of kernels, and therefore the name multi-kernel. If we look at the history of computing, the first computers were taking an entire room or even more, and they were barely capable of running a single application or computing algorithm. So there was no room to share or run multiple applications. But as systems ramped up in capabilities, in performance, in computing power, it became possible to run more complex algorithms and sometimes to even share the time of that system, because there was also an increasing demand to be able to run more applications there. So it moved slowly from a single user system to a multi-user system, or at least multi-application system, where sharing time became necessary, and the need for an operating system to organize this sharing became also necessary. As systems became more connected and eventually became portable and embedded, more and more security, safety, performance, and also power management concerns came real. A famous, let's call it conflict, was between Andrew Tannenbaum and Linus Torvalds. Andrew Tannenbaum is a researcher at the university and the creator of the Minix operating system. And in the early days of Linux, one of his famous saying was that Linux was by design outdated, even in the beginning of its existence. As an answer, Linus explained that, Linux is more portable than Minix. Minix is a notable microkernel design, while Linux is a notable monolithic design. So in the end, who was right? Well, actually both. Andrew Tannenbaum was and still is right that from a design perspective, the monolithic design is not going to allow anyone to build a robust design and a scalable design. And therefore, Linux is not really the cleanest architecture. But at the same time, and history proved him right, Linus and the decision to put everything together in Linux inside the kernel, including the file system, the network stack, and so on, and all the drivers, had become also an easier way for everyone to transport Linux and all its middleware into new platforms and to make it more hackable in a good way, of course. It's actually a trade-off here. On the monolithic operating system, everything is together and it becomes easy to add or remove a component and to make a component talk to another component because there can be direct calls or organized call and easier data sharing. But that data sharing also means that by design, everything can crash if there is a malfunction in any of those components. So the robustness of the entire platform depends on the weakest component, the weakest driver, in the monolithic kernel. Applications are isolated, but middleware and device drivers are not. The microkernel operating system takes an entirely different approach, where the concept is that only the minimum amount of services run privileged inside the kernel mode or inside supervisor mode. Everything else has to run in user space in an application. That includes, of course, regular applications, middleware like Unix servers, file system, network stack, and so on, but also device drivers where this becomes possible. Microkernels are elegant because everything is running as a thread. The consequence of running everything as a thread is that you can schedule them. So all drivers by design on a microkernel are actually schedulable, and it becomes possible to give them more or less priority, to maybe limit them in terms of time, and to understand the entire scheduling of everything. Everything is running in user mode, which means that if there is a crash in a driver or a stack, there is a higher chance that the system will not entirely crash, or at best, that service will become unavailable, but the rest of the platform can continue to work. Of course, this resolves the CPU, the general architecture, but there are still caveats. One big caveat is that advanced devices can use DMA and can copy data without going through the CPU from the main memory to the main memory or to the physical world. You need some protection to be able to make sure that a device driver running as an application is not going to be able to corrupt the entire platform. Typically, the way to manage that is either to split the driver or to use an IOMMU. Interrupt handling is slightly higher latency because you have to deliver the interrupt event to a user mode, and that means the kernel has to send that notification to a thread. So of course, there is at least the context switch to that thread. And to some extent, there is always some level of code that needs to remain in the kernel. The interrupt controller code needs to remain in the kernel, for example. But still, the possibility to organize the memory, a memory hierarchy and separation between components on the platform makes it a clear advantage for the stability, the robustness, and the scalability of the design in terms of memory. So that clears about space partitioning. How about time partitioning? Well, there are several techniques to establish a possibility to limit a process or a group of processes, or really technically a group of threads, so that they cannot take more than a certain amount of time in a certain period. Some approaches, like ARINC 653, go with a very fixed period of time. Some other approach in a more flexible way, but harder to determine, like Linux C groups, QNX adaptive partitioning, or AMCOS time partitioning, just try to establish a limit to the amount of time that an application can use, or a group of applications. There are also other aspects that have evolved over time, like the fair scheduler on Linux that tries to be not very real-time or deterministic, but tries to make all applications get their fair share of CPU time. In the embedded space, there is a clear position that real-time schedulers make a lot of sense because there is no need for fairness, but a need for determinism, where you can clearly determine and identify who will run at which time when something happens. Originally, the CPUs were single core, but as the complexity of system increased, it became possible to have multiple cores on the same CPU and to make them work together as a multi-core platform. Naturally, the operating systems evolved from single-core schedulers into SMP schedulers to do multi-core scheduling. But still, the same database of threads was used in that multi-core scheduling. And that means there is a limit to the amount of parallelism that can happen in that particular table of management of the threads, because there is only one core at a time that is capable, that should be capable of modifying that database, that table, by design. So there is some kind of spin lock, and then another core can take over that spin lock or that lock to be able to modify the thread state. And, well, as a consequence, there is some level of interference between the cores. A little bit more in detail, what you see on the left here is the SMP operating system design used by most operating systems on the market today. SMP stands for symmetrical multiprocessing. In this SMP design, there is a single database or table of threads in the entire platform, and the communication and the change of the thread state requires the acquisition of the global kernel lock. In this one, the thread 1 will acquire the kernel lock, then send a message and notify core 2, which will also try to acquire the kernel lock after thread 1 on core 1 has released it, and send a message to thread 2. This works fine. However, if another thread on another core wants to do also an IPC, an inter-process communication or an inter-core communication, to send a message to another thread, this will have to wait, because either core 1 or core 2 have the lock. When those two first cores have released it, then thread 4 can actually acquire the lock and the communication can continue. So there is some level of concurrency, but the parallelism is not there. When true parallelism is required, the typical way to go around this limitation is the use of the AMP design. AMP stands for asymmetrical multiprocessing. In this AMP design, multiple instances of the operating system actually run. Then the cores managed by a single instance of the OS still go under a global lock, but they do not impact other instances of the operating system. When threads want to communicate locally or within the operating system, then the communication can go like before in the SMP design. However, when they want to communicate across operating systems, they need to use a specific operating system API or middleware API to communicate. One that is actually the big limitation of AMP, where the application needs to be aware of the location of the destination in the of the message that he wants to send. In the multi-kernel design, each core has its own local table of threads, and there is no possibility for a core to acquire a lock that will impact another core. So when an application will try to prepare a message to unlock a thread on another core, the thread will talk to the local scheduler and the local kernel to send a message to another core in an asynchronous way, and that will at worst impact only the sender and the receiver core, and in many cases will actually not lock the two cores forever. And that means that by design, another core who wants to send a message to yet another core will equally be able to send a message without impacting other cores. So here, with the multi-kernel design, you have a true parallel behavior. This performance topic may seem like a detail, but in reality, that can have a significant impact on the performance of your platform. AMdahls Law states that the increase of performance of any given system can only go up to the fraction of the platform that can truly go in parallel. In today's system, we already have 4, 8, 16, or even tens of or hundreds of cores. And a typical system in the embedded world today, or the PC, is already reaching 8 cores. One would expect that when you have 8 cores, you would get 8 times the performance of a single core system. But in reality, when you only reach 80% parallelism in the system, the performance increase is only just above 3 times. Then when you consider a system where you have truly independent applications running on the platform, where these can effectively run in parallel, they all rely on the same component, which is the operating system. So it becomes a key component that to the performance of the platform that the operating system is capable of running in parallel. The multi-kernel is therefore quite useful and important. Actually, the multi-kernel is a pretty recent invention in the history of computing. Around 2010, the first published papers became public, and the first notable, or the most notable, operating system was published by Microsoft Research under the name Barrelfish. The conclusion, however, was that the POSIX multi-kernel is too slow. One of the reasons is that they took the multi-kernel and especially the concept of message passing really to the letter, and is implementing a complete POSIX implementation and framework only through very pure message passing became impractical. There are other multi-kernels available. One of them is, for example, Microkernel that you can find, and it's mainly used in mainframes, where the executive is really a tiny scheduler that is really the microkernel running next to a Linux to do the real computing execution. Then you can find AMdahls POSIX and its extension for hypervisor, AMdahls Hypervisor, which can scale from little cores like Renesas RH850 up to ARM v8A cores, Cortex A50 or A70 series, as well as Calray MPPA, which has some components going up to 80 or 256 cores. And AMdahls POSIX has also been safety certified. And we have measurements that demonstrate that it is really faster than Linux. In order to compare the multi-kernel implementation of AMdahls POSIX with another kernel, which is the performance operating system like Linux, which already has a pretty optimized implementation with also an optimized libc. When you look specifically at synchronization mechanisms like condition variables, mutexes, semaphores, barriers, and so on, what we observe is that the performance of Linux may be acceptable, but the performance of AMdahls POSIX is significantly better, especially when there is a contention, when a thread may have to block or was blocking and can be unblocked. The performance of AMdahls POSIX can be 2 to 4 times faster on average and go up to 35 times faster in the specific cases. In the situations we have measured, this performance is always as good as Linux or significantly better. This is the execution from an API perspective. Another aspect that is not shown on this slide here is the context switch time. On a typical SMP system, the scheduler may need to acquire the global kernel lock to schedule, which means that only one core may schedule at a time. On AMdahls POSIX, with the multi-kernel design, each core is always free and available to reschedule its own local threads easily without depending on any other core. So the context switch time does not increase with the number of cores in the platform. To conclude, there are two main aspects that the OS evolution has improved. From a memory management perspective, it has become clear that memory partitioning and the microkernel design is making everything more robust, and also more secure and more safe from a functional safety perspective and from a high robustness perspective. And most new operating systems on the planet that intend to be serious about robustness actually have a microkernel design. Now, from a scheduling perspective, SMP has been the most common design for being practical. However, it is clearly not the most efficient, and the multikernel demonstrates that it can scale better by bringing better parallelism to the platform and higher performance in general for the same SoC, same chip. Memory partitioning and time determinism are clear trends. Thank you for listening to this presentation. If you want to know more about it, feel free to contact us at the contact details that you can see on the screen. Thank you very much.